Alright everyone, so in this video we're going to be talking about how different things can affect solvation or how quickly it dissolves. So in our previous two videos we talked about how a solution is something that has a solute and a solvent, something's being dissolved, and how that actually dissolves, so whether or not it is undergoing solvation and dissociation, or solvation only, is based on whether or not it's ionic or covalent, and you can check out those other videos in order to get more information, but different things are going to impact how quickly dissociation and solvation actually happen. And so one thing to keep in mind is that solvation only occurs when the solute and the solvent particles actually collide. If they don't actually touch, then there's nothing for them to happen. They have to come into contact with each other. So for example, if I'm dissolving sugar into water, or for example, these pictures that we drew up here, this sugar with these waters, if they don't actually touch each other, then this part can't actually happen. And so there are three common ways to increase the collisions that occur between the particles. And these are going to be pretty familiar to you because if you've ever made Kool-Aid or sweet tea or any kind of beverage where you've mixed something, then you've probably done this. And so when we are increasing the collisions, what we're doing is we're increasing the rate or the speed that the solute will dissolve. And so the first way to increase the rate or increase the number of collisions is through agitation. So this could be stirring or shaking. So for example, if you've ever seen one of those water bottles that have like a little plastic ball with like little edges on it, or maybe it's a metal looking whisk, that is used so that when you shake the bottle up and down, it blends in like a protein powder or something along those lines. And it's to increase the collisions between your solute and your solvent. Now, the second thing that you can do is to increase your surface area. Now, the way that you increase your surface area is by breaking by breaking the solute into small pieces. So if you have small pieces of sugar versus a actual cube of sugar, the small pieces have more exposed surface area, which allow the collisions to occur. You can think about this. This is why we chew, right? This is why we use our teeth to chew our food, because if no one puts a saltine cracker in their mouth and just leaves it in their mouth and waits for it to completely dissolve. We chew it, we break it down into smaller pieces. And so increasing our surface area is a great way. So keeping in mind that small pieces are going to dissolve a lot faster than big pieces. And the last thing is when we increase our temperature. Now, with temperature, it's going to speed up the movement. And this is because temperature measures the kinetic energy of a atom or a particle. And so the faster it is, the faster those particles are moving, and they have more energy when they collide, so they're going to dissolve a lot faster. And so temperature, though, is really special because it impacts solutes differently based on their state of matter. So we know that solubility is affected by raising the temperature of the solvent because of that kinetic energy we were talking about and how it's going to cause more collisions at a, compared to a low temperature. But if you're a solid compared to if you're a gas, raising that temperature is going to have two different effects. So when you raise the temperature of a solid, then increasing your temperature will also increase your rate of dissolution or your rate of solvation. And so that's good. This would be called a direct relationship, meaning as one goes up, the other goes up. If you decrease temperature, you decrease the rate. This is why you typically, if you're trying to make Kool-Aid or sweet tea again, that you would use warm or hot water to dissolve your sugar rather than cold water. This is also why if you try to add sugar to iced coffee, it's not going to work out well for you because it's just going to dissolve really slowly or not at all. Now, with gases, however, when you increase your temperature, you actually decrease your rate of dissolution. And this is because they have an indirect relationship, and actually increasing the temperature decreases the amount that can stay dissolved. Increasing the temperature means that they want to get out of that liquid. So these are going to have opposite effects. Now, another thing that can impact your your rate is pressure. Now, pressure is only going to affect the solubility of gases because increasing the pressure of a gas solution pushes the particles close together. And this is going to mean that there are more particles per volume than at a lower pressure. Basically, it's increasing your density. Now, keep in mind that pressure is a force. So anytime, let's say if we have a can here and there are atoms, anytime those atoms move, and they're always moving around, and they hit the side of the can, the inside of it, they're exerting a force on that can, which builds up and is what we know as pressure. And so when you increase your pressure, that means you increase the rate of solvation for a gas. But if you try to increase pressure, it's going to have no effect on solids at all. Increasing, the force on sugar doesn't actually help it stay dissolved. No matter how much I push on it with my spoon or something like that, it's not going to change how much it dissolves. Now, both temperature and pressure play an effect when we're making a soda. Remember, a soda is a solution, where our solute would be the sugar, it would be the syrup flavoring, it would be the carbon dioxide bubbles, and our solvent would be the water that it's all being dissolved in. And so if you do the steps out of order, then you actually are going to change what happens and really impact it. The soda has to be made in a particular order. So the first thing that you would need to do is to heat your solution. So you'd want to heat the solution to dissolve, the sugar, because sugar is a solid and it needs a hot water or warm water at least in order to dissolve as much as it can. And once the sugar is dissolved, you can cool it down without the sugar actually coming out of the solvent. Now, with step 2, we would want to cool it down, so cool the solution, okay, to dissolve the carbon dioxide gas, because in order for the gas to dissolve, it has to be cold. But when it's cold, the sugar, again, stays dissolved. But we know that not all sodas come cold, right? Sometimes when you go to the grocery store, it is warm and it's sitting on the shelf. And so the way that soda manufacturers protect their soda from becoming flat before it ever reaches their customers is they add pressure to it, meaning that they add a whole lot of more carbon dioxide in there than is actually necessary, and they put a lid on it. So they add pressure and, seal it. They put a lid on it, and this means that no matter what temperature it is, that carbon dioxide is staying dissolved because there's literally nowhere else for it to go. It's being pushed into the solution. And so just keeping in mind that pressure, temperature, and agitation are all going to affect not only how much gas or solid can be dissolved, but how quickly that occurs. And so in our next video, we're going to talk about how we measure these and the solubility graphs and concentration. So keep an eye out for those videos.